This is Maths Linear Algebra Tutorial 7, Question 5, number 18. In these questions, we have 18a to f. Again, we are answered true, false. The first question states that if B is in the column space of A, so we have AX equals to B again, and B is in the column space of A, meaning B belongs to the column space of A, then the solution of AX equals to B is a least squares solution. The answer is true. In fact, it is not only a least squares solution, it is an actual solution. The least squares solution is an actual solution because x hat found will be such that AX hat will be exactly equals to B. We now refer to section 7.1.2, page number 4. Let us see the slides. Refer to this figure 1. It states that if B happens to be in the column space of A, then B is AX for some x. And what it means is that for example, this is no more the vector that we are wanting. The vector that we are wanting is exactly lying on the space of the column space of A, and therefore AX hat would be the desired solution. In 18b, the question states that the least squares solution of x equals to b is the point in the column space of A closest to B. An initial reading would fool you. Here, please be careful. He's talking about the least squares solution. He's talking about x in AX equals to B. The closest point in the column space of A to B is B hat. B hat is closest to B. To achieve B hat, we use AX hat. So the answer to this question is false, because it is B hat that is closest to B, not the least squares solution, which is X hat. To see our slides, please refer to 7.1.3, page number 3, figure number 2. Let us now go to this slide. This is the slide we are talking about in page number 3 of section 7.1.3. B hat is in the column space of A. It is the closest point to B. To achieve this B hat, we use X hat. X hat is here. When we move around the X in this space, we are moving around the B solution. So please have a look at this slide to understand the subtle differences. In this question, it says that the least squares solution of AX equals to B is simply a list of weights that, when applied to the columns of A, produces the orthogonal projection onto B. Basically, he's talking about AX hat, and we can view X hat as simply weights multiplying by the columns of A. And we have x1, x2 to xn if we have n columns of A, because simply it is a list of weights applying to the columns of A, because we are doing x1 multiplied by A1 plus x2 multiplying by A2 and so on, xn multiplying by an to achieve B hat. Why is this equals to the orthogonal projection of B onto A? Please refer to section 7.1.3, page number 3. We'll now go to this slide. Read these slides carefully. The theory states that given the normal equation, and when we solve for the normal equations, we are getting the least squares solution, and the least squares solution is the same solution as the best approximation theorem, which is basically projecting B into the column space of A. In this question, question number 5, 18D, the question states that if x hat is a least square solution of ax equals to b, then this is the way to get x hat. On first reading, you might think that it is true, and in general, this is true provided ATA inverse exists. But when ATA inverse does not exist, we still can calculate x hat, as in the tutorial, this tutorial number 7, question 3, we found that when ATA inverse does not exist, we still can find x hat, a least square solution of ax equals to b. So in this case, the answer to this question is false. For detailed reading, please see page 7.1.3, page number 4, theorem number 17. Let us now turn to this slide. So we have seen this before. This is page number 4, theorem number 14, which states that if the columns of A are linearly independent, then we can find x hat through this equation. Else we are unable to find x hat through this equation simply because ATA inverse does not exist. And we have to use other methods to find x hat. In this question 5, 18E, the statement states that the normal equation, which is ATAX equals to ATB, the normal equation provides a reliable method to compute the least square solution. What he's implying is that x hat equals to ATA minus 1 ATB is used to solve for the least square solution. From theorem number 14, we found that this might not exist, and since this might not exist, then therefore this is not a reliable method to compute the least square solution, because sometimes we have columns of A being dependent, and when that happens, this inverse does not exist. In the last question, question 5, 18E, if A has a QR factorization, so basically we have AX equals to B, A is factorized into QR, X equals to B, then the best way to find the least square solution is to do this, which basically means that we remember that Q has octonormal columns, so Q transpose Q is equals to I. What we get is Q transpose Q are X on the left hand side, therefore Q transpose B on the right hand side. Once we have that, we basically throw away Q transpose Q because it becomes I, the identity, and now if R is invertible, we apply R minus 1 on the left hand side as well as R minus 1 on the right hand side, and we now get X equals to R minus 1 Q transpose B. And it says that is this the best way to compute the least square solution? And again, the answer is false, because actually we do not like to find the inverse of any matrices. We note that R is a upper right angle matrix. So this is R and this is Q. We now remember that when we have an upper triangle matrix, we can solve actually by back substitution, as in the previous tutorial 1 and 2. Basically, we solve from the lowest variable first. For example, if we have x1, x2, and x3, we will solve from x3 first by back substitution, finding x3, putting it into equations associated with x2, and finally x2 and x3 variables are plugged into equations for x1 for the upper right angle triangle. So we never want to perform an inverse because sometimes it is unstable. That's it. So the answer for question F, 18F, is also false. Thank you.